Okay, today I am going to give you the lecture on 2.2, hydrodynamic relations. Some of you might feel, well, we learned this already in the fluid mechanics and fluid dynamics, but my purpose doing this is quite different. And what I'm going to do is just review the conservation law. And after we get the three conservation law, conservation of mass, conservation of momentum, and the conservation of energy, then of course that will define the pressure density relations. Then from that point, I'm going to, using the approximation, develop the underwater acoustic wave equations, which is the, I really like that because that's a physics. You don't really working in the abstract space, but in the physics space, you know all the hydrodynamic relations to derive such equations, then reduce down to underwater acoustics equation. Then you could say, why underwater acoustics equation? You could say you should develop into the shock wave equation. But I'm going to use acoustic wave equation, listen carefully, as approximation or good, the best fit approximation to get all the necessary equation for the underwater shock wave. The idea is this. I mentioned to you before, I hope you really remember that. If this is a ship or submarine, if explosion occurs very next to the target, when I say target, which means a ship or submarine, there is nothing to mitigate the shock, there's nothing to protect the ship or submarine. Submarine will have a hole regardless, nothing to design for. So we are, for the survivability is concerned, the explosion, if it's too close, that's the end of it. But has to have explosion a little bit away from the hull, okay? Then you can discuss about the survivability. So US Navy or Korean Navy, they are not considering the explosion very next to the hull. Okay, so away from the hull, by patrol or search, you have to detect the ship or some other target from the terrorist. You have to search and get that location and the threat correctly. Okay, so in that sense, underwater acoustics equation is very good enough to use it for the shock wave, the approximations. Okay, don't confuse it. So that's what the situation you are always working on it for the shock is concerned. So here, hydrodynamics relations, I'm quickly go through, but I want you to recollect your thought, but should be easy, but still you have to pay attention. Basic assumption here is ideal fluid, and ideal fluid really means no shear stresses, no heat transfers in there, no discontinuities in pressure, fluid velocity, internal energy, okay? Then you're dealing with 3 a conservation law, the conservation of mass, conservation of momentum, and conservation of energy, then pressure density relations you can get into there. First, the conservation of mass. But recollect your understanding, this may be the last time you will face. For someone, this would be a first time. Conservation of mass. Considering a small fixed region of the space, this is water, particular point you are considering, fix the region of the space in the interior of the fluid. Then you are considering the differential volume, dx, dy, and dg, and totally you can say the dv. Then conservation of mass says any change in mass of fluid, any change in mass of the fluid contained in the volume is equal to the net quantity of the fluid which flows through the boundary surface. So when you consider the cube, how many the directions you have? X direction, flow in X direction, Y direction, and the Z direction. So we're going to do one direction at a time. So change in mass m in time t, resulting from the change in the density at the point xyz for the differential volume dv, which is dx, dy, dg, can be expressed as delta m is change in mass, okay, is equal to delta rho times dv. So it's a time variation, so you can say it's equal to del rho over del t times dt, then differential volume dx, dy, dg, okay? So now you go through one direction at a time. So UVW is, I said, is a velocity of the point. When I say velocity of the point, this is a fluid particle velocity. UVW is a fluid particle velocity, okay? It's not the equal to the wave velocity, okay? Fluid particle velocity. Moving with the fluid in the XYZ direction. But first, let's consider the motion in X direction. This is like a flux. Rho u in X direction at X phase, right? This for differential, the differential volume, you have X phase and X plus dx phase. In other direction, you have the Y plus dy direction, dy phase. Then Z direction, you have a Z plus Z plus dx direction. So flux rho u x direction first. This is x direction. Then once you do this y direction and z directions, the formulations are same. So this is mass per unit area per unit time. Okay, mass per unit area per unit time in x direction. Okay, so that's a rho u x. Then differential is concerned the rho u x phase minus rho u x plus dx phase at time dt. Then dy dg is the surface normal to the x direction for the differential volume. Then this is equivalent to minus. Why is a minus? For differential is concerned, this term has to go to first, this goes to second, so which is identical to saying minus del rho u over del x dx dy dg at time duration dt. This is a delta mx, right? So here is a change in mass in x direction for dy dg, differential surface, and in time dt. And you can do the same in y direction and z direction. So you have delta mx, delta my, delta mg. If you add together, that's equal to delta x, which is due to the change in the density, mass density. Then you plug in each equation set. Then you have so-called conservation of mass, or another name is this is the equation of continuity or continuity equation. So which is del rho over del t plus del rho, the v is equal to 0 for the simplicity. So divergence is concerned. This is called divergence. This is you know all this. So divergence is concerned the del dot, the rho, you can say simply del dot is a divergence, scalar product. This del is what? What's a del? 성태, what's a del? Henschel, what's a del?
Vector operator.
That's a spatial operator, right? This is a spatial operator. So this guy is equal to del x I plus del z plus del z k, right? That's a gradient. It's called a gradient, right? Gradient operator. It's simply operator. And scalar product, then rho is a scalar, v is a vector. What's a v here? This is a fluid particle velocity. Fluid particle velocity. So v here is equal to ui plus vj plus wk. Jk is unit vector in x, y, z direction. So it has a name in it. So del dot v, for example, that's called the divergence. Result is when you have a scalar product, then result is a scalar. So this equation, remember, I want you to remember this equation, not memorize it. If you love it, you will remember. You will never forget your 여친, 남친 name for whole your life. I don't want to really see it's in the video tape in there. So conservation law or equation of continuity, remember this. But you don't have to memorize, it's all always in there. But what happened? I told you for underwater explosion wave, shock wave in the water, you could deal the rho as a constant in space. For the constant in space, this is a del operator is a spatial operator applied to rho. If rho is a constant, let's say rho is a constant, I can say this is rho naught. When I put the naught, which means a constant. A lot of places I use the subscript naught, which implies it's a constant. In other words, you have a fluid for the explosion, underwater explosion study. I can say the fluid, the mass density is constant all over the place. So which means I can take them out. This is a constant. I can take them out the outside of the del operator because this is a spatial operator. So I could say del T plus rho naught del dot V is equal to 0. Okay? But del rho over del T, this is not equal to 0. Why? If if you think, oh, this is a constant, del T, then if I set the constant, what does it mean physically? It's not compressive. This is equal to 0. Water doesn't, the shock wave doesn't propagate. So if shock wave doesn't propagate, it's done. You have nothing to solve. Okay, it's all fixed. So if I just put the shock wave here, this is a T, this is rho maybe, then nearly constant, but there is a fluctuation. That's what the underwater acoustic wave signifies it. So del rho over del T is not equal to 0. That's a compressive. But rho naught, magnitude-wise, is really nearly constant. Everywhere in the water is nearly constant. When you apply the spatial operator, then you can take them outside. Conservation, so that's what conservation of mass, we'll use it, okay, to derive the underwater acoustic wave, which we'll use as underwater shock wave, on the assumption that we are not considering the wave, fluid wave motion close to the hull. So conservation of mass. Conservation of mass is concerned, is right here. Conservation of momentum is equal to the Newton's second law. mx double dot is equal to the F. That's what the Newton's second law is. So this time you are considering the forces acting on the volume dx, dy, dg, moving with the fluid, not fixed in space, it's moving. Then you are considering the pressure. At one side is dx, the other side is the p, x plus dx. This is all only in x direction, but you can consider y direction and the z direction. So vector sum, you can have it. And ax is acceleration of the differential mass is equal to du over dt. So this is x direction, u is fluid particle velocity in x direction, okay? But this is a total derivative, not the partial derivative. Then again, as we have done in conservation of mass, a similar approach, we're going to first do the x directional motion, then y directional, then z directional. Vectorially, you can add together. So net force, this is what the Newton's second law, which is really same as conservation of momentum. Net force acting on the element in x direction is equal to mass times the acceleration. Same thing. Then this is minus, then rho dx dy dg. This is a differential mass times the x directional accelerations. So then you can just cancel the terms. You have rho du over dt is equal to minus del p over del x. Your remembrance is coming back? No? Still far away? You have done this before, can't you? So you can you have the similar equation in y and z direction, right? You replace u by v and w, and you change x to y and z. The vectorially you can add it together. So if you vectorially add together, the left hand side is rho dv. This hat, all the days, when I use Macintosh, I talked to a few people to remember. I couldn't put the superscript. That time, no option. So I want to put the arrow at the top. I can't do it, so I have to put the tilde. Such a era is not 100 years ago, no. It's about 1985, 86. There is no options. So I put the tilde. It's all tilde. This is a vector, just signifying there's a delta. And over here, this is equivalent to this is in next page, okay? Derivation is there. This is total derivative. Then you can expand into the summation of the partial and another term. But I said that this term is approximately equal to 0. It's coming in next section. Gradient of the velocity. This is a fluid particle velocity. Gradient, spatial variation is very small. Almost for underwater explosion, almost none. So the fluid particle velocity itself is very small. Okay, it's not 1500 meter per second, very small. Small times the gradient, very small, then multiplied, too small. Then you can just ignore it, okay? Second term. As a good approximation for underwater acoustics problem. So that's why I just introduced here. You can really set this is equal to 0. Then when you add x directional, y directional, and z directional motion, so if you do the vector sum, this is simply the minus gradient p. P is here you can say really shock pressure, okay? So that's what happens. So derivation of this from here to here is shown in the next page, because velocity is a function of spatial position, which is x, y, z, and the time t. Okay, so here is nothing but the chain rule is what I apply here. then dx dy, dx dt, dy dt, dz dt, which is u v w. Okay, and this is just a carry over. Then you can come down here. There's two terms. Simple derivation. When I write a long time ago, I put this, and then I feel I'm not that happy, so I just redo in different fashions. But this is all that is. Okay, so y-directional equation, z-directional equation, take a vector sum in x, y, z direction, then you have pretty important conservation of momentum equations. Okay, so conservation of momentum equation. So this is one equation, the second equation. So over there, rho dv dt is equal to minus gradient p. Okay. Conservation of momentum equation. So what's the last equation? Yes, sir. Conservation of, who cares? Hunter, what's the last equation for conservation law?
Momentum conservation?
This is a conservation of momentum equation. That's what we did. This is a conservation of momentum equation. Don't feel strange. Corgi, right? Conservation of what? Momentum equation. What's the last conservation law? Energy, conservation of energy. Energy never disappear. Energy is always there. Change from one form to another. It's always there. So last conservation law is conservation of energy. Okay? Is it coming back or still fuzzy around up there? Should it be coming back? Please, after you study, regardless of what topics, when you really keep studying, it's all converge into the one point. It's all same. In other words, whether you study fluid dynamics, whether you study the structures, whether you study heat transfer, thermodynamics, final equation set is all similar each other, very close each other, form is concerned. So no differences. Conservation, last conservation law. This is all expanded form. It's not the additional equation. This is all conservation of momentum, expanded form. But you can reduce down to that form. So simple. Okay, so simple. But if you expand this like this, and the conservation of energy, I'll read very slowly, then digest it, then equation makes sense. We're going to consider the element of volume. I'm talking about dx, dy, dg. Moving with the fluid, and enclosing of fixed mass of the fluid, okay, total energy per unit mass of the fluid. We are dealing with the energy per unit mass. Unit mass means 1. Total energy per unit mass of the fluid consists of kinetic energy, we want to say Ke, and internal energy, whatever it exists in there. E is internal energy, K is kinetic energy due to the motion or fluid particle velocity itself. And internal energy, which is sum, is talking about the internal energy. Internal energy is a sum of thermal and any chemical energy. Any internal energy is the sum of the energy in there. Then the conservation of energy is identical to saying here total change in energy is equal to total work done due to the pressure. Okay. Then once you just get this, then in time dt and the element of the volume dx dy dg, then the change in energy in the time duration dt, d E plus internal energy plus kinetic energy over dt, during the time duration dt, this is a differential mass, because energy was spelled out per unit mass, so you have to multiply rho times dv to get that total energy in that volume. Maybe too easy, so you might feel why he does again. But it has a reason, as you will see. Then in time dt and the element of the volume dx dy dg, change in energy spelled out like this, then this is equal to, just to carry out the differentiation, then this is the first term, this is the second term. Where's the mass here? Where's the mass? Kinetic energy is half times m velocity square. What happened? No m here. This is kinetic energy is per unit mass of 1, right? So m is all 1, then m handled in the differential mass is handled right here. Make sense, right? Say yes, yes. Then work done, now this is a change in energy, is equal to the work done. First in x direction due to the pressure P. So P applies in x direction, which means dy dg, phase of differential volume. So this is a force times velocity times dt. This is a distance. So force times distance, work done. So simple physical terms. So as a result, work done on the two phases of the volume. First, in x direction, same as the conservation of mass and momentum, and the difference of the force, dt, dy dg, you can express like this. Then that's x directional, And you have, you can do similar way for y directional, almost identical, right? This one and that one. And this is for, oh, this is x is the same as that one. This is for y, and this is for z. So if you then add together, this is right hand side, this is a left hand side, total change in energy, then reduce down to that form for conservation of energy. But you can simplify it. You can simplify this portion down here, this portion down here, scalar dot, and this portion is minus the gradient dot p. This is not rho, this is a p v vector. So then you can derive some other useful expressions. You just carry out the just differentiation applies to here, next applies here. Once you apply differentiation in the first v, then plus the second v, then you will have, you can delete the half because two terms in there. Then right hand side, first apply divergence to p, next apply the divergence for the v. First p and first v, second the v. So this apply divergence to p is here, and next applies to here. This is very straightforward, the algebra. Then you can bring back the equation of continuity. You have all my arrows and note, right? Yeah. So that's easier how to go in there. So from here, you can get into that forms. You can bring out this. Then you have this. Then this term is equivalent to say d rho over dt. The derivation is in the next page. On Monday, I'm going to hand out the really booklet, which he put everything all together and made is a complete note for index. So you don't have to print from now on. You will get the paper copy. Then use it, that's better. So that's what we're going to do. It's, I'm not going to cover whole that page because this is only 6 weeks out of 16 weeks. So, but you have complete underwater explosion notes, my notes, but we'll cover the 6 weeks amount of lecture. So this is a derivation. Then it reduced down to this equation. It's a very precise derivative. Okay? And this is a final conservation of energy. This conservation of energy, 3, which is rho dE over dt is p over rho d rho dt. So this is the third equations over here. This equation has total 3 parameters: internal energy, and the pressure, and the mass density of the fluid. So you can tell 3 parameters: P, rho and E, okay? So that signifies this relationship. You can express E as a function of the rho and P. So over here, for the pressure density relations, internal energy E can be expressed as a function of the pressure and the density as a thermodynamic variables, and this differential can then be written as this. Two parameters you can express for the internal energy. Okay. It's very nice. Then, but this is implicit expression, it's not the explicit expression. Then take the variation, this is all I'm doing over here. From the conservation of energy, bring back down this equation down here, then change the forms. dE, differential, the internal energy is equal to P over rho square times d rho. Then you can say, just showing the different forms down here. So this is implicit relations, but I can easily claim that I can solve P as a function of the rho, where the initial value of the P and rho are known, and E, P, rho, three parameter, the relation, if the relation is known from the thermochemical data, then it's doable. But it's implicit relations among that. But I can claim that for the given internal energy, of course, P can be expressed as a function of the rho. Very important showing the relation, because this is important in the underwater acoustics, to derive underwater acoustics equation set. Okay, so this section 2.2, you don't have to study much, but after you go back over the weekend, I want you to go through and fully understand what's going on in the hydrodynamic relations as is. Then I'm going to use all this relation to express the underwater acoustics wave equations, okay? Any question? Simple. But Kyung-seok, maybe some of you didn't take the fluid mechanics stuff. Civil engineering, but still civil engineering, they take hydraulics and right, Kyung-seok, you're in civil, right? You're in undergraduate, they are taking the fluid mechanics, right? I remember I took when I was in undergraduate. What about Songtae? You took, right? Undergraduate, 예술? Everybody at least take one course. That's what I did. Hyunchul, you took the course in undergraduate. Abdullah, Bangladesh, regardless, you can avoid at least one course in fluid. This is all the basic conservation law in the fluid. Remember, UVW is a fluid particle. You are dealing with the fluid particle velocity. And for underwater now, with the information we just talked and learned for hydrodynamic relation, I'm going to go into now develop the underwater acoustics equation. Then after we got the underwater acoustics relation and equations, then we're going to solve that equation. Then we're going to have beautiful solution set to be used for underwater shock calculation. That's the whole purpose. Usually in undergraduate, when you're dealing with a wave, you start from the wave equation. Have you ever derived the wave equation? You start usually the wave equation, and solution, general solution set is already available saying this is a wave equation and this is what the general solution. Now go ahead and solve for the particular wave. That's what you do. Sometimes not make sense. So here, what I did, so I'm in the position to develop the equation to be used for underwater, the wave propagation and underwater wave reflection. So then, of course, I want to develop the wave equation. If it's a plane wave, it's going to be simple. If it's a spherical wave, then it's a little bit more work. And regardless, you have to solve that wave equation. Then you solve it. Then you get the final solution set, which is a beautiful solution set that shock people, underwater shock people should know 100%. But as I really giving a lecture to many shock expert, most of them, I cannot say most, a lot of experts didn't know that. Relation between the shock wave pressure, and the fluid particle velocity. That relation you must know. That's what I'm going to drive out here. Whether you are the gas explosion specialist or fire specialist, I demand the relation. Just using the one equation, P is equal to rho C V or rho C U. This, if you ask me, do I have to memorize it? My answer is yes. So important. All you learned from Young Shin, maybe this. Okay, what's a P here? Shock wave velocity. Shock wave at the time of explosion. Shock wave propagate. Bang, out there. Then rho is what? Yonghyun, what's the rho? Louder, I can't hear you. Yeah. Fluid density. I would rather say the fluid mass density. Same, but mass density is clear. It's not the weight density. Mass density. Mass density. What's the C? What's the C? Kalgi, what's the C? Louder. Acoustic velocity in the water, which is about 1,500 meter per second. And V is what? Underwater acoustic velocity? Abdullah, what's the V there? Particle. See? Fluid particle velocity. Very important. This is good for the plane wave. Okay, plane wave. I'm giving you consequence first to elevate the importance of the equation. When you solve wave equation, you will get that. That's what we're going to do Monday. And you have additional term, so-called the surge term, additional term, if the shock wave is spherical wave. There exist only two waves, the plane wave, one-dimensional wave, or the spherical wave. If explosion occurs and shock wave propagate in the radial direction, as the shock wave front is moving farther away, R goes larger and larger. Eventually the curvature approaches to what? Approach to plane wave. So secondary term, this second term has a lot of meaning for when the curvature is small. But as R curvature is getting, the radius is getting larger and larger, then importance of the second term diminishes away, disappears away, okay? And second term there for spherical wave, which is a function of proportional, second term is proportional to 1 over R squared. I give you consequence first, then so on. Okay, so it's 2.3. This is only about 10 pages, or it's not much. How many pages is this? About 10 pages. So I think next to maybe a couple lectures, the chapter 2 are going to be all done. And the chapter 3 is more fun. Chapter 4 is good fun. Chapter 5, a lot of fun. Okay? So that's what you should expect. Okay, if you have any questions, see me, talk to me anytime. Okay? So I'll see you Monday morning. Have a nice weekend. I think it's a rainy weekend, look like. Okay. Good day.